this green suit.
All right, guys, I'm going to go ahead and get started. Oh yeah, if you wear the green suit in front of the green screen, you're just a floating head.
Yep.
What I was saying though is, if I've got a nice bright background, you can see.
It was weird.
You can well, it's just more light coming off the screen here. So.
Of course, now it's kind of going back to dark, so it could be it's just an auto adjust.
All right, well, let's get into the shell. And I did grade quiz 6, and I realized that when I first put the thing together, I wrote the word orangutans, and most of you wrote orangutan, or orangutan, and so you got it wrong, but I fixed all those. So thanks for doing that. And I also realized I sent an email out to Rachel, letting her know, well, asking her if maybe she couldn't see Eddie's presentation because a few people missed the leather gloves aspect, and it could have been that people just didn't see the leather gloves in the video.
Oh, yeah.
And then there was also, I just wasn't clear if I caught that on video. And the other thing that came up was the black bag being a legitimate reason for not sorting through the, so but I want to make sure that was actually there, because I don't want somebody to miss points because of our video capabilities.
That monkey missed that. We didn't go back and watch the video, so I don't know if it was captured.
Yeah, it's okay. All right.
You were the production made it the best choice.
Yeah.
Well, that one, if you hadn't seen it, you would not have known.
If you're really trying not to watch the videos, that's what you get.
All right, so I got one unread post, and
Thermodynamics at the end of the world.
it's very interesting. So what's, yes, that is correct.
Working title was abandoned all those.
It doesn't matter if you follow the money in the world, as you're going to burn it, fuel,
I'd be rich.
I've been trying to get
Here's all the, that's all that I would do on. Just don't have any word. Well, when I did it ever since, just after a while, how much wheel spinning do you want to record?
Okay, so team, here's what I want to cover today. Hopefully you had a chance to watch this video. Basically, the upshot of this video is that the bottom line, or the theme, if you will, is that the universe is constantly heading towards a state of greater disorder, like it or not. The fact that we're discussing organic matter recycling this week is especially critical to this video, and I'll tell you why. And I'll go over my own little version of the second law of thermodynamics, and then tell you how I think, well, it's not my version of the, well, actually there are multiple versions of the second law, so everyone can have their own version as long as they're not contradicting the theories themselves. But what I want to share with you is how it relates to recycling. So let's start here. Go to the journal. So we're looking at NRGY 270, and it is 11/12/15. So what I want to cover is second law. I want to cover the life contradicting the second law, and I'll just put a question mark to that. Contradicting the second law. And there's a really neat book out there if you get a chance, and this is totally relevant for organic matter recycling, which again is the theme of this week, is Schrodinger. I want to say 1956, What is Life? That's the title of his book. Schrodinger was a quantum physicist who took a shot at biology. And then I want to look at old versus new biomass. And then finally, I want to look at the economics of wood chipping. How's that for a going big to small? And the reason I want to do it in this order, just yesterday, I was sitting in my house, collaborating with a colleague on a renewable energy project, and we were just hearing the biggest noise you ever heard right outside the window. And what is it? Well, it's a tree company taking down a tree, right? So they've got 2 chainsaws running, they've got the truck idling, and they've got the, I don't know, I'm just going to say 1 to 2, it might have been as big as a 400 horsepower motor, grinding through these 12-inch logs. I mean, it was a Bandit 432, and so you're pumping, and it's also very relevant to our own Earth tub. Like what is being burned or consumed in order to process the biomass. So that's going to be what we cover at the end. They were going to sell 13 cubic yards for $150, and they were going to sell that as mulch, but they were perfectly willing to have me just show up with my wheelbarrow and take as much wood as I wanted to, for free. Just to get it out of the neighbor's yard.
Before they chewed it up?
What's that?
Before
they chewed it up. Yeah, I was grabbing it for firewood.
Mm-hmm.
So we'll do that economics problem at the end. So first, let's look at the second law. Let's look how life may or may not contradict the second law. I'll briefly mention Schrodinger, and then old versus new biomass, and I want to look at that through the lens of I'll find it here. I'm just going to write SH. I'll think of it in a second. It might even be SCH, etc. University of Georgia, 2015. It's a new paper. I discussed this a little bit in 102, but it has tremendous implications for recycling technology in 2015 and kind of the big picture.
Is that the salvage logging biomass for?
What's that?
The School of Georgia?
Oh, no, these guys, and again, I'll remember his last name here in a second. They have taken a planet-sized view of biomass on planet Earth, start to finish, similar to what we do in 101, but with a slightly different twist. They throw nuclear in there, and they look at old biomass versus new biomass. And old biomass is just natural gas, coal, and oil. It's just sequestered carbon of things that were living on this planet a really long time ago. So, okay. And then finally, and again, we did the aluminum can problem already, and every single one of your challenges and hurdles in recycling technology is going to come down to money. That's the way our society, civilization, constitution, government functions. Okay, so second law, let me just start out with this thing called entropy. And entropy, the symbol for it is S, and if you have a heat engine, and most of the engines we use, like our internal combustion engines, coal-fired power plants, nuclear power plants, what have you, are heat engines. And what happens is some heat goes in. Q is the symbol for heat. Q has the same dimensions and units as energy. heat is energy. So I'm going to write Q. I'll put brackets here. The dimensions are mass per length squared per time squared. So this might look kind of funny to think of heat as mass times length squared divided by time squared, but when it gets right down to it, that's what it is. Heat is energy. So heat goes in. I'm going to call this Q1 to some box. And this box is your heat engine. Wood chipper, leaf blower, car, coal-fired power plant, you name it. It's a heat engine. It has to get hot to work. And then some heat comes out. We'll call it Q2. Right? That's the exhaust. That's the smokestack. That's the chimney. That's the tailpipe. Q2. That's whatever heat's coming out. Now, HE equals heat engine. And this stuff has been known since 1852. Sadie Carnot. So this is Carnot. It's Carnot. It's Clausius. It's Kelvin. And it's also Boltzmann. Those are the pioneering physicists into the second law. Now, why would you heat something up only to get some, junky heat out? Well, it's because you want to get some work out of the system. Work also has the same units and dimensions as energy, mass over length squared over time squared. And if you remember back to NRG 101, we did this a bunch. We just said that there's kinetic energy, that's mass times, 1/2 mass times velocity squared. Well, there it is. There's your mass. Length squared, or length over time squared, is your velocity squared. So right there. Now, what else is going on in this situation? Well, you've got some fluid going in. This is going to be your air and your gasoline going in. It's going to be your CXHY plus your O2 heading into the system. And what's coming out? Well, your H2O, your CO2, right? So there's your combustion products going in, combustion products going out. Doesn't matter. And we talked last time about the fact that the majority of organic matter is CHON, C-H-O-N, and we're looking at 3 of them right there. The other one, obviously, is nitrogen, because we're talking about the atmosphere heading in, and so also coming out, you might have some NOx. Hopefully not too many. That's the greenhouse gas that we're always worried about. So there you are. C-H-O-N, CHON, fits in perfectly with the lecture that I gave on Tuesday. Now, what comes out? Well, if you're spinning a shaft, you might have tau omega. So here's you got some torque, and you've got the angular velocity. Well, what's that good for? Well, it's the drive shaft on a car. It's the shaft on a steam turbine in a stationary power plant. It's the chain drive on your chainsaw. It's whatever. There's some spinning element that's doing the work. It's also worthwhile to note that power equals W dot equals tau omega. Now I'm going to apologize for the lack of number of symbols in our language. That's a big W for work. And this guy is just a little, it's an omega, so a smaller W. So let me just go ahead and I'll put the little uppercase deals for big work and just a little lowercase for omega. Now, the dot is the same as this. The power equals the change in work over the change in time. And if you remember from NRGY 101, that's just the definition of power, work, and energy. I'll just write it this way. Energy equals power times time. And it's also probably worthwhile to go ahead and write, since we already know that work and heat have the same units as energy, we can just write them all like this, one big happy kind of thing right here. So if you know how much heat, how much work, how much energy, that's the power times the time. Now, we also know that there's going to be some temperature coming out the bottom of this machine. So there's going to be some Q1, which is the heat going in, and that's going to be happening at T1. T1 is going to be hot. It's going to be something on fire. T2 is going to be cooler. And if you run your system properly, you're going to get T2 down as close as you can to atmospheric pressure. To atmospheric temperature. So think about your fireplace at home. Everyone's like, oh, fireplaces, they're so inefficient. They actually make your house colder. Well, why is that? Because there's so much of that heat just flies right up into the sky. Some of it comes off as radiation, some of it stays in the ceramics as convection, conduction, but a lot of it just right up into the atmosphere. But if you've got one of these condensing boilers, the H2 is going to head up. It's going to condense in the stack. That heat is going to be in there, and it's going to come back down. And you're actually, when your furnace is done doing its thing, you could put your hand over the top of the furnace at the exhaust, and that's a more efficient system. So, efficiency just equals T1 minus T2 over T1. So the big, and I've gone through this conversation many times, efficiencies in coal-fired power plants, nuclear power plants, there's somewhere between 30 and 40%. Same thing in your car engine. If you can get 30 or 40%, you're doing great. 25% is kind of more the norm. But the idea is you got to get T1 as hot as possible in order to increase the efficiency. There's no way around it. It's just the second law of thermodynamics. Okay, so now we've got a notion of what energy is with heat, with work. We also just mentioned temperature. Okay, what does that have to do with entropy? Well, if we draw our little system again, we've got Q1 going in, that's hot. We've got Q2 coming out, that's cold, and we've got our work coming out. We've got T1 and we've got T2. The change in heat equals Q1 minus Q2. Pretty simple. So whatever goes in minus whatever comes out, that's the change, and that's approximately what the work is. Like where did that heat go? Well, it got turned into work. It got turned into a spinning shaft, into a moving car, into electricity, etc. So where did it go? Well, it got turned into work. Plowing the field, whatever, dragging a plow back and forth across a field to plant crops. So entropy now, so as heat flows through this system, you're also going to have a change in entropy. And what the heck is it? Well, the change in entropy equals the change in the heat divided by T2, divided by the ambient temperature at where this is. So T2, I'll just write this down here, T2 equals T atmospheric. It's the temperature of the surroundings. All right. Now, the important thing to note is this is always positive. All right, it has to be. That's the only possible way to do work in a heat engine, is to have something hot, do some work, and then something cold comes out. I hope you got that from the video. So delta S is greater than 0. Nobody's found a counterexample yet. Well, maybe one exception, and that brings us to the second point of the lecture. So, another way of thinking of entropy is like so. And this is actually a really good example. Let's just say we have some piston, and this is more or less what a reciprocating combustion engine is. You've got your hydrocarbon, CX, HY, and your oxygen flowing into this chamber. And we looked at that oxygen data a little bit on Tuesday, the Mount Loma, Mauna Loa, whatever it is in Hawaii, showing the decrease in atmospheric oxygen. So oxygen goes in. Where'd the oxygen come from? Photosynthesis. There's some little bug or plant out there making that stuff for us. It's here initially. Everything's kind of nice and tidy. You've got your engineered product. Here's your technosphere going in, right? You've processed this petroleum, and here's your here's your biosphere going. So the technosphere is coming in, the biosphere's also coming in. Remember I showed my little video, my little figure last time where you had the biospheres over here, technospheres over here, somewhere in between. Well, right there in that combustion chamber are those two spheres colliding. That oxygen came from nature, that gasoline came from our technologies. They collide right in that chamber. The piston goes down. Work comes out, and now you got a big old mess sitting in there. So you went from this kind of nice, tidy, organized, you know what that is, In one half the chamber, the explosion goes off, the diesel engine squishes it, or the spark plug does its thing, and now, and then finally off comes the exhaust. Inside here is your T1, your hot temperature, and outside coming out is your T2, and there comes the work. So, delta S greater than 0. The other important upshot is this. This is happening over and over again through time. So it also means that delta S, the change in entropy over the change in time, is also greater than 0. What's that look like as a plot? Well, looks like this. Here's time. Here's entropy, and it goes up. Can't do anything about it. Now, the neat thing about life, and I'll show you the Schrodinger book here in a little bit, the neat thing about life is that life is always trying to do this with itself. Life is always trying to beat the second law. So, for example, it would be highly unlikely. So, there, I'm just for example, we could probably go out into the dumpster out back, find enough food, enough grass, enough cardboard, enough trace metals, and in that dumpster would be, in terms of a mass basis, enough to form an organism, right? Enough and actually form a cat or a plant. I mean, just in terms of the chemistry sitting in there, but it's not going to do that on its own, right? It's not going to happen. What you have to do in order to get life to be life, is put in some kind of energy. Where does the energy come from? Well, photosynthesis. It's food, right? It's just, it's food, it's sunlight, it's the things that we as organisms need to survive. Different things to different plants. I mean, plants wouldn't know what to do with a cheeseburger any more than we would know what to do with a photon. Well, I guess, we do get a little bit of effect from photons, but you can't just stare at the sun and forget to eat and stay alive. So when life is sort of bending this entropy curve down, the rest of the universe is experiencing a bend of the curve up. So you can think of this as oxygen coming into your lungs, combining with the carbon in your body, and CO2 going out. You can think of this as, I'm trying to think of something that's just with your own body. Oh, you can think of yourself on a hot day, you're sweating, so the steam is coming off of you and adding entropy to the atmosphere. So organisms are always entropicizing the environment so they themselves can stay orderly. And let me show you one last thing quantitatively on this topic. This has very big implications for organic matter on planet Earth. Papers, entropy. This paper has not been published yet. It's been accepted for publication, so I'm showing you a preview. If you guys think your homework and grading is a pain in the butt, this thing took me about 4 years to get published. It was, I got kicked around with a few different journals. They're like, what the heck are you talking about? No, we're not interested. Finally, the Wessex Institute picked it up. Who knows what impact it's going to have? There are things that get put out there in the literature and nobody reads them for 50 years, and then someone's like, what? Oh my, someone actually was thinking about this junk a while back. I threw a few little curves into this paper, but what I want to show you is this, and we were just talking about Ray Kurzweil earlier and his kind of acceleration models, but what I want to show you is the rate at which human civilization is doing this, bending the entropy curve up, is a trillion times faster than nature would do it on its own. So you can't avoid that curve. And you could think, gosh, that sounds really fast, but if you think back to the 101 and 102 lectures, we are burning through fossil fuels 10 million times faster than they were put here. So we're talking some pretty big numbers. If we were around to burn those fossil fuels, they would just stay there in the ground as a nice, organized, very dense carbon source rather than being burned and sent into the atmosphere. So the number I came up with, and I think I've got it written out here. There's that exact model I was just showing there with the engine a second ago, hydrocarbons going in. The little twist that I mentioned that I put on this paper is that in most systems you also have information going in and information going out. It's true in our brains. It's happening right now. I'm talking, you're listening. Maybe sometime later you'll convey this conversation to somewhere else. Same exact thing. The Google car is constantly sucking in bits of data from the environment, pumps it back out to the internet for people to see. So you've got organized chemistry coming in, disorganized chemistry coming out. You've got some bit stream coming in and some bit stream coming out. Let me see if I can find the... Okay. So in this paper, I actually reference a conference paper that I gave in December, And so I said a trillion trillion. It's not quite that much. A trillion trillion would be 10 to the 24th, but it's 1.8 times 10 to the 23rd times greater than the background rate. And the way I came up with that, I just took the fact that we dump 500 exajoules of heat into the atmosphere per year. And so just going back to this very simple equation, so this is Leighton 2015. I've got, again, you've got delta Q over T. What we're looking at in this case is 500 times 10 to the 18th joules, and this is per year. And then the temperature of the atmosphere, it's like, let's just look it up. I can't remember off the top of my head. And you've got to do this in Kelvin. Atmospheric temperature. And the atmosphere does not have one single temperature. It has a mean or an average temperature, but we'll do our best here. Temperatures vary, of course they do, we know that. Let's see. Surface temperature. Let's just see if we can hit that. Atmospheric temperature range. Because you have to pick something. There it is, 57 Fahrenheit. 287 Kelvin. I was going to poke right around 300 Kelvin, but 287, we can go with that. Divided by 287 Kelvin. Anyway, what that gives you is an S dot. It gives you a delta S over delta T. What do I mean by that? Well, it's just this. It's the slope of that curve. Here's your delta S. Here's your delta T. It's how quickly entropy is increasing on planet Earth as a function of time. And you can do that, and I'm not going to go through all the math because I did a similar calculation for the background rate at which entropy is being produced in the universe, and that's more or less just the total radiation of all of the stars, off into space, kind of, heating space, if you will. So anyway, that's where I came up with this 10 to the 23rd. What's that mean? Well, I don't really know specifically what it means. I do know if you, and these were done very early in biology. If you sort of lock an animal in a airtight cage, it will eventually die because it's going to be basking in its own waste products, right? I mean, that's kind of what it's doing, and that's kind of my fundamental concern here is the rate at which we are entropicizing the Earth. And I just did it from a thermodynamic standpoint. You can also look at it, plastics in the ocean. We talked about aluminum in the biosphere, et cetera, et cetera. At some point, you just are basking in your own waste, and you can't survive. So I'm looking at entropy as sort of a waste product that we need to really, figure out on a fundamental basis going forward. Okay. So back to the original. So life is somewhat contradicting the second law, but only locally. You're never going to beat it globally. It's always there. It's always going up. Take a look at Schrodinger's What is Life? So there's Edwin Schrödinger, 1944. And he was not a biologist. I think this is just a little bit here. But what he comes down to is that they did this whole aperiodic crystal, like DNA being something that's, and we looked at DNA, phosphorus a little bit, looking at something that's almost periodic, but just different enough. Everyone's got a slightly different DNA pattern to be unique. Somewhere down in here, he starts to talk about the fact that in order to stay alive, energy has to be pumped into living organisms. Anyway, it's a fun read. It's not overly technical. It's not going to bog you down with a whole bunch of math. Okay, so check that out. We have now covered 2 of the 4 things I wanted to cover, and we'll just take a quick little break since we're at 35 minutes.